Está grabado. Se la usaba en su contra.
Cacha, ¿cómo está quedando?
Ups, fue mi teléfono. Let me write the title.
¿Los plumones están buenos?
Si se ve poco me avisan. Let's see. Yeah, I think this. Yeah. No. Dejémoslo por aquí.
Está bueno. Te lo dejamos aquí.
Avísame si es que no se ve. Era el mejor, pero el que más sucia. That's fine, I can just. You can go ahead whenever you want.
So it's a pleasure to have once again Sebastian talking about Heki and
Heki distribution. Thank you very much, and thank you for staying until the very last lecture. So today I just want to finish describing the equidistribution properties or asymptotic distribution properties of Heki orbits. So just to remind you what we did yesterday, so we said that over CP there is this natural decomposition using the modular interpretation of this space as we can decompose this space in three pieces. The piece of bad reduction, and then there's the good reduction that splits into two other sub pieces, which is the locus of ordinary reduction, and then supersingular reduction. And yesterday we did this case using Tate's uniformization theory. We proved that for a point with bad reduction, there is this uniform distribution result, but it's with respect to this Dirac measure on the canonical point on the Berkovich space X canonical over CP. And I tried to describe yesterday what this space looks like. We said that it's topological space which has better topological properties compared to CP because CP is totally disconnected. Sorry, I have to do this briefly. And then I'm not able to reproduce this picture, which is the typical picture that one sees when people are talking about Berkovich spaces. So somehow in this picture, CP is here. It's like with this analogy of writing the upper half plane somehow has some kind of completion of the rationals. In this picture, the CP points, the classical points are in here, and all these lines, they represent kind of geodesics on the Berkovich space, and this is just one part of the Berkovich space. It's just the points which are below the canonical point. So the canonical point is somehow here. It's outside the CP. And somehow joining the canonical point with a classical point, it corresponds to basically taking the unit disk and then decreasing the radius until it becomes like a single point. And then in terms of seminorms, which was this abstract definition of the Berkovich affine line, this canonical point corresponds to the Gauss norm, which is defined in this way. Just as a reminder that the abstract definition was in terms of seminorms on polynomials with coefficients in CP. And yeah, this is a very, I think, nice illustration. And it's a very kind of complicated tree. There's these points where you have like infinitely many branches. So it's not like a nice graph with just finitely many edges coming out of each vertex. So it's a bit more complicated. So I just wanted to show you like this picture. And today it's about the Hecke orbits for points with ordinary reduction, and then at the end, points with supersingular reduction. And then, yeah, that's the goal. Hopefully, I will manage. OK, so now we do Hecke orbits in this ordinary reduction locus. So here, I should say that we will have, again, the same kind of result, but the proof is completely different. Here we use, as I said before, the uniformization theory of the multiplicative version by Tate. And we cannot use that theory for points which are not in the bad reduction locus. But still, we can use other tools. So let me first phrase the result in this case. So as we did yesterday, this can be phrased in terms of convergence of measures to the Gauss point. But now we'll just phrase it again as a result about counting points in a small disk. So the result is as follows. For a point E with ordinary reduction, we have that for every disk of radius r contained in the ordinary locus with small radius, let's say r less than 1. We will do again this counting. We take the Hecke orbit of a point. We look at the points which are in this disk. We take the degree somehow to count the points which are here, and then we divide by the total degree of this divisor, T and E, and then this goes to 0 again as n goes to infinity, which means again that every time I take a small disk, somehow the points in proportion, they escape from this small disk. Yes, please.
Can you remind me what you mean by a disk in ore?
Yeah. So I forgot to say, let me remind you that there's this nice description of these 3 pieces using the J invariant. So under the J invariant, this corresponds to OP minus finitely many residue classes, which correspond to the supersingular elliptic curves in characteristic P. And the supersingular region is just a complement, so it's exactly the union of B1, blah, 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 Bm. So yeah, so this is a union of infinitely many residue classes, one for each point in FP bar. And I'm removing just m of these. And m is the number of supersingular elliptic curves. So m is the number of supersingular elliptic curves over FP bar. Yeah, that's what it is. So I'm always using this identification using the J invariant. So here we will use the fact that Hecke orbits in general Hecke operators can be splitted because they have these multiplicative properties. So we know that from the theory of Hecke operators that T n m equals T n composed with T m every time we have coprime indices. So for all n and m coprime. And for us, it will be important to split Tn into the p power part and the part that is coprime to p. So we write, in particular, Tn as some Tp to the k composed with T and 0, where p does not divide and 0. And then, because of this simple reason, we can treat these 2 different cases independently and see what happens. So let's start with the case n equals n0 coprime to p. So we are going to look at a subsequence of this sequence where n is coprime to p now. And we are going to prove this result in this case. And later we will do the case where n is a power of p. In this case, we are going to use that there is a nice property about isogenies. So let me introduce a notation that will be relevant today. So I will put of sub n of E1, E2 will be by definition all the isogenies from one elliptic curve to another of degree n. So this is just isogeny of degree n. And okay, this is just one important definition. And then here we use that the reduction map that goes from n torsion of my starting elliptic curve E. There is a reduction map to the reduced curve, also to the n torsion points. This is also a group morphism, so this is just reduction. This is actually an isomorphism, so both groups are just Z mod n Z square. So this is an isomorphism. Hence, when I'm taking the n Hecke orbit of E, I'm taking the quotients by all subgroups of order n, which will be contained here. These different subgroups will reduce to different subgroups in the reduced curve. So that will allow me to count, do the following counting trick. So here is important that p does not divide n. When p divides n, this is no longer true. I will say that again later. So now I will do the following. So our disk, BR, so remark, this small disk of radius less than 1, it has to be contained in some residue class, which is not one of these by this identification. So this BR is contained in some residue class. Let me see what notation I'm using here. B0, I guess. B0, a residue class different from the BIs. That corresponds, that reduces to a single point with respect to reduction. So by definition of residue class, this will reduce to a point, J0 in FP bar, which again I'm identifying with the elliptic curves defined over FP bar. Hence, this number is just the J invariant of some elliptic curve defined over FP bar. And now I can do this counting trick, this very simple. Oh, shoot. So I can count the number of points in the Hecke orbit TNE which lie in B0. This will be larger, of course, than, let's say, if I do BR. This will be less than the same degree. I don't have to put this now. Degree of TNE on the residue disk sigma 1n. I'm just increasing the disk to a residue class. And this I can compare to the number of isogenies of degree n from E tilde to E, maybe I call E0 this one. Because of this fact that there is a good, this reduction of the subgroups that I'm taking the quotient with, there's a, they correspond to different subgroups in the reduced curve. So this allows me to do this counting. And now I just have to count how many isogenies I have between two elliptic curves, which are ordinary over FP bar. But what is this? This is this set of isogenies of degree n. It's easy to see, or it's part of the general theory, that this is like a group of rank 2 because of the definition of ordinary elliptic curves. And the degree map, the one that is given the n here, is a quadratic form.
Without it.
What? What did I say? Oh, sorry, without n. Yes, yeah. Sorry. Yes. Thank you. And the degree, which gives the n, right? It's a binary quadratic form. So it's not difficult to construct a bound for this number. It can be like a very silly bound, is just square root of n. So the number of degrees, the number of isogenies of degree n between e tilde and e0 then will be bounded by some constant times n to the 1/2. This is a really bad bound. You can put actually n to the epsilon. It's much better. But for the purpose of this proof, I just need whatever which has an exponent less than 1, because I'm dividing by sigma 1 of n, which is at least n, this part. And this is bounded by, let's say, n to the 1/2 in this case. So this goes to 0. And we are done. In this case. Yes? This? It's just like write any binary quadratic form, like ax squared plus bxy plus cy squared, and look at the possible solutions, like integer solutions of this binary quadratic form equal n.
It's a positive definite.
Positive definite, yes. Yes, yeah, thank you. So positive definite. Yeah, there are only finitely many solutions, and one bound, one bad bound is this one. Yeah, already the x has to be less than the square root of n, and once you fix x, the y is determined. So it's a very simple bound. Nothing deep here at all.
How do we construct this B0?
B0? Okay, so this is because this is a small disk of radius less than 1, and the residue class is any open disk of radius equal to 1. Anything that is, any disk that is, has a radius less than 1 is contained in a residue class. I'm just using this fact. Yeah. Basically, you take the reduction of this with respect to the reduction map that I'm using all the time. The fact that you go from OP to OP mod MP, which is FP bar. What I'm saying is that the reduction of this thing is just 1 point. Hence, it's contained in a residue class. Yeah, thank you. So keep asking questions, please. OK, and now we're going to do the much more interesting case when n is a power of p. So now n is a power of p. It's not surprising that this is a more interesting case because we are doing p-adics. So let's see what happens in this case. Now what I just said here, that the reduction map gives this isomorphism, is no longer true. So what's going to happen is that the map that goes from n torsion to the n torsion of the reduced curve is just surjective, but it has a kernel. This actually, because we are in ordinary reduction, one equivalent way of defining a curve with ordinary reduction is that this reduction has only, sorry, I want to do p here. I will do only p first. This p-torsion group has less points than what we expect in general. So it's just one copy in this case of set mod p set. And here I should quickly say that we will use this other property of Hecke operators is that TPK is essentially given by TP in a polynomial way. So it's like TP composed with TPK minus 1 minus PTPK minus 2. If this is correct, hope so, yes. This is for all exponents, at least 2, I guess. So somehow the study of these Hecke operators can be reduced to essentially to the iterations of TP, essentially. Okay, so we can just iterate TP. I will put it in quotes. We can just iterate TP. This is not exactly what one has to do, but let me, for the sake of simplicity, just say that, okay, instead of doing TPK and k going to infinity, let's just do TP and iterate TP. Okay. And now, the thing that's going to happen is that, just let me recall the definition of TP. It was this taking the quotients of EC, where C is any subgroup of E of order P. And this one has P plus 1 possibilities for C, so has degree P plus 1. And in this theory, there is a canonical choice of one of these possible C, which is called the canonical subgroup. And this canonical subgroup is very easy to define. It's just the kernel of this map, because this goes from a group that has P square elements to a group that has P elements. So the kernel of this map has P elements. And this is one distinguished subgroup in this list. So let's say, now I cannot use orange. Let me just do it like this. Here, let's just put H of E will be defined as the kernel of that map, of the map that goes from EP to E tilde P. So this is one distinguished subgroup. So H E is called the canonical subgroup of E. So we have one canonical choice. And then with this one canonical subgroup, we can define a branch of this correspondence, of this divisor. So we can define a T map that will go from ordinary elliptic curves with ordinary reduction to elliptic curves with ordinary reduction, will be just taking the quotient by this one special subgroup. So this is a map, a well-defined map. It is actually analytic if one think of this as a subspace of CP. So there is a notion of an analytic map. One has to prove that this is analytic. It's not obvious. It's analytic, and also one can prove that this map is, what's the word? Contracting. Contracting. And the key property is that TP of E can be written as, this is one of these, so TE will be one of these quotients that I'm taking, and the other ones are just the preimage of E. So this is an analytic and contracting P to 1 map. P to 1 map, which means that it sends generic P points to just one point. Every point has P preimages if you count them with the multiplicity. So there is this very interesting formula for the P Hecke operator. Has one canonical branch, and the other one is the inverse of that. And the important thing is that since this map is contracting, you expect this part to be the opposite. So if this is contracting, the branches, the preimage should be repelling. So this part should be kind of repelling. And because this part of this Heike orbit has more points than this one, this is just 1 point, here there are p points, the dynamics of this correspondence is dominated by this part. So it's essentially take 1 point and start computing the preimages. And then you have many, many of these points. And then because this is a repelling kind of map or correspondence, we are going to get exactly what we expected, that points will kind of escape from any small disk and will try to escape to the boundary of any disk. So this will prove that that if I do the number, if I compute the proportion of points which are preimages, let's say tk, of E, and then I'm thinking of this as a divisor because I have to take into account multiplicities of preimages, and then I restrict to some small disk of radius less than 1, and then I divide by the total number of points, which will be p to the k, I think. But we expect is that this goes to 0 as k goes to infinity. So this will prove, again, convergence towards the Gauss point for iterates of TP, but because of this, you get the result essentially for TPK. Not essentially, actually, you get it, but maybe not in this naive way. You have to be more careful with this relation. Okay, but it's just to give you an idea of what's going on, and now you start seeing that here there are really things that are only make sense p-adically. So this map, it's p-adic analytic. You can only define it using this canonical subgroup, which is only defined using the reduction map for the p-torsion, which doesn't make sense in the complex setting. Okay, and I don't think one expects to have a branch of Heike correspondence that is defined in such a large space. You can only do it locally, I guess. Okay, so this is the idea sketch of the proof in the ordinary locus. And now I can move on to the most interesting case, which is the supersingular reduction. R is fixed, yes.
This is based on the RS compact.
Sorry, and what?
Why this? Well, how do you know this goes to 0?
Because I'm using this is just, I'm waving my hands here. I'm just using that this is a repelling, right? So basically, so let's say I'm in one residue class. Sorry? So there is this small disk of radius r. I'm trying to prove that points do not stay here. In proportion, they go away, right? They go to the boundary of this. Let's say there's just one residue class, so that's easier. So essentially, T, what we'll do is will be a map that actually has a fixed point in the center. There's a point here. It also has a special name. It's a canonical lift of This will be a fixed point. This is, let's put it like T star or something. I don't know how to call this guy, but we'll call it like this. E and an arrow, because this is a canonical lift of the ordinary elliptic curve. This will be a fixed point by this map. So essentially, all points, if you iterate with T, they are convergent to this fixed point, but I'm doing the opposite. There might be some points that remain here, but the proportion goes to 0. Yes.
And how do we? I'm sorry if this was already.
Yeah, no, go ahead.
How do we obtain the key property? Is it because it seems
Oh.
very unnatural to me?
Yeah, it's not at all trivial. Okay. What you have to do, I guess, so this is work, I think, I don't know if this is the first, Dork was working on this kind of things. I guess what you can say is that you can recognize in TP that there's always one branch which stays away from, how can I say this? When you look at the p-adic properties of this operator, you recognize that there is one branch which is apart from all the other points. Okay, there's a way of measuring this. And then because this is, this I didn't say before, that I should have said this, this is an algebraic correspondence. This really comes from algebraic maps between modular curves. Hence, any branch of an algebraic correspondence, you expect this branch to have good analytic properties, like this, what is it called? Implicit function theorem, something like this, you know? Yeah, maybe it's not a very convincing argument, but I should say that it's not trivial. So it's not like I'm saying, like, this is not like a remark or anything. By the way, this is also related to something that is called the Ashler-Shimura congruence relation, that when you reduce mod p, the p modular polynomial, there's a nice factorization of this, like x minus y to the p, x to the p minus y. And somehow that's also related. This is like a lift to CP of this mod p relation. Again, I'm waving my hands to kind of give a very not precise explanation. Yeah. Okay. And now, Hicke orbits in the supersingular reduction setting. Now, yeah, please stay here. In the ordinary, in this case? So in this case, I'm saying that, okay, somehow I forgot about the whole Hicke orbit. I just look at the preimages under this p-adic analytic map. And I'm saying that if I look at the preimages of a point, they will not stay in a closed disk. In proportion, they will all be outside. So every time I take a small disk of radius less than 1 inside a residue class, in proportion, most of the points will be outside. So they are trying to escape any small disk. This is the statement. And this is equivalent to this convergence to the Gauss point. So really they are not convergent to anything in CP. They're escaping everything. Does that make sense? It's going to the Gauss point, but this is, I guess, the confusion. They are not converging in CP. You have to look at this Berkovich space, and they're kind of escaping from any small disk becomes equivalent to converging to this point, which is outside CP, and is in this Berkovich affine line.
So in this case, you can also write a statement like in the...
Yes, it's the same statement. So the deltas of the TNE converge to delta in the canonical point. It's the same statement in a more simple way, I guess, without using Berkovich. Yeah. But it's equivalent. Okay. And now supersingular. So supersingular region is a union of, I don't know, m residue classes that correspond to supersingular elliptic curves. And now somehow the TP, the powers of P will be, in a way, easier. We will have the same result. So again, now we have, if I do the degree, I compute the degree of the Hicke orbit TPK E restricted to a small disk of radius less than 1 divided by the total degree of this guy, then this will again converge to 0 as k goes to infinity. And this is because essentially I can do the same argument because there is a phenomenon of overconvergence. So this T is only defined here, but it can be extended a little bit to the supersingular region. So let me give you, again, waving my hands with this. The reason is that we can extend T that was originally defined only in the ordinary reduction setting to not two supersingular elliptic curves inside the locus of supersingular reduction. So this, again, as I said, is an analytic map, and somehow you can extend the domain of convergence a little bit more, not to cover the whole supersingular reduction locus, but part of it. So this not two supersingular elliptic curves, I don't really have time to go into the details, but I will say that in these residue disks, they are not, there's like a distinguished center for each one of these points. They are not close to these centers. They remain like far from the two supersingular points. So let me define this as not two supersingular inside the supersingular regions, the region, and this is a proper contention. So T can be extended to this domain, and the important fact is that since I can extend this map to this region, the image under T of this not two supersingular elliptic curves will be all of the supersingular region. So again, T, P, K will be like T to the minus K. Because I cannot define T everywhere, but I can define the inverse map everywhere. Okay? And again, I will use the fact that instead of looking at TP and iterates of TP, I can essentially work with the inverse map. And again, I'm using the same arguments that T will be kind of repelling. So I will be able to show that the Hecke orbits of any point with supersingular reduction still converges to the Gauss point. Or if you don't want to use this formalism of Verkovich spaces, you just think of this in this way. Like they don't stay, they escape from any small disk. Everything here is, I'm using a lot of results which are quite deep. There is a very precise way of measuring how supersingular a point in this locus is. For this, you have to use actually an Eisenstein series of weight p minus 1, at least if p is 5 or larger than 5. You can use the Eisenstein series of weight p minus 1 and think of it as a function on elliptic curves together with differential forms, and use this Einstein series, the values of this Einstein series on elliptic curves to kind of measure how supersingular these points are. But this is really, I will skip all of that because I don't have that much time. And I really want to finish because there's one more case that I have to cover in the last 20 minutes, which is Hecke orbits with supersingular reduction, but now n coprime to p. So finally, E has supersingular reduction, and p does not divide n. So I can no longer use this branch, because now I'm not going to look at TP, So what can we do here? Let's see what we did. Let me try to remember now. OK. So let's do some simplifying assumptions. So fix one of these residue classes. This residue class, I will call it BE, because it corresponds to the residue class that reduces to the J invariant of E. So this reduces the J invariant of E under the reduction map. So this will be the disk that corresponds to E. OK. And now, what is BE? I will just use some fancy words, but please don't be discouraged. So I will think of BE as a deformation space of E over OP. Basically, what I'm saying is that E is the reduced curve, and I'm looking at points in this disk as all possible lifts. This makes sense by definition of this residue class. And then there is a theory that says that, OK, the deformation theory of a supersingular elliptic curve to a ring like this is equivalent to, and this is a big statement, I guess. There's a lot of important mathematics behind all of these statements, that this will be isomorphic to the deformation space of something else. I will deform the formal group of this guy, Fe over OP. And what is Fe is what is called the formal group of E. So it's not really important if you have never seen formal groups. I'm not going to need the definition of this object. But the basic idea is that every time you have some kind of group law, let's say, let me say like this. Let's say you have a Lie group, and then in a Lie group you have, by definition, a group law. And if the Lie group is analytic, you can think of addition near the 0 element as a power series in 2 variables. And then the formal group is essentially that power series. So it's just like a formal power series that encodes the group law of your geometric object. Anyways, somehow we have to go from this deformation space of the elliptic curve to the deformation space of the formal groups, because somehow these spaces are nicer in some sense. And this I will call BE as before, but with a hat. And these were these kind of objects or spaces were studied by Gross and Hopkins. And one can give a lot of properties about these deformation spaces. The important thing is that in this space, this is more like a space that has a natural action. So there is an action of the group of unities of RE, where this RE is by definition the endomorphism ring of the formal group. So these are all the formal morphisms from here to here, from Fe to Fe. But this is an abstract definition. You can think of this as taking the endomorphism ring of my original supersingular elliptic curve and doing a process of p-adic completion. And what is this? This is, well, if you remember what I said, I think it was maybe 2 lectures ago, we said that this ring, when I'm in supersingular reduction, this one is like a lattice of rank 4, because it's a maximal order in a quaternion algebra. So this one is like a p-adic space set p to the 4 power. Okay? Okay. and then I'm looking at the units. So everything here has a structure of a quaternion order, and here the units are those elements whose quaternion norm is invertible. Okay. And now what are the important properties? So I'm doing a lot of kind of abstract bananas, but I have to go back to Hecke orbits, and I have to try to recognize my Hecke orbits as orbits under the action of this group. Even though this is a big group, it's a p-adic group, it's not finite. And Hecke orbits are just finally many points. So what we are going to do is the following. So this is again key fact. Important results is that the endomorphism ring of E embeds in this RE. Oh, this part is easy just by tensoring. But now the important thing is that if I take isogenies of degree n and P does not divide n, then this part, the isogenies of degree coprime to P, of degree n coprime to P, they will go to units. Because the degree here will correspond to the quaternion norm here, and that if the quaternion norm is a p-adic unit, then the element is invertible. And so this is 1, 2, and 3. Now we go back to T and E is essentially, I'll put it in quotes again, one has to be more precise, is essentially I'm looking at, this is a finite set of elements, and I'm acting under whatever I said here that it was a natural action of this thing. It acts on the formal group associated to this one, to the starting elliptic curve, which is a point in B, E hat. So capital E is an element in this deformation space of little e, hence the formal group of capital E is also an element in the deformation space of the formal group of little e. So everything here is contained. This is the action of these elements here. This is contained in the B, E hat that I'm saying here, just waving my hands, that this is kind of BE. There's a lot of identifications, and many of these things actually are not isomorphism. I have to take a quotient by some finite group, but one can control all of that. And now, what is the beef of all this discussion is that Hecke orbits I'm recognizing now as some kind of a collection of finitely many elements in this group acting on a given point. This point is fixed. This is a point that I'm not moving. I'm just moving the n here. So it's not difficult to convince ourselves that what we have to understand is how this varies inside this p-adic group. Okay? So this relates to, is the formal group of the elliptic curve. So every time I put a beautiful F, this is the formal group of the elliptic curve. There are two, right? So every elliptic curve has a formal group. So that's why this is the formal group of the little e, the reduced curve, which is I'm not moving because I'm fixing my residue class. And I'm doing everything here locally. And this is the formal group of the capital E. It's another formal group. Yeah, does that make sense? Okay. Okay, so what I say is that at the end, we need to understand the distribution, so the distribution of the sets end and E, which are finite, is a finite set, inside this p-adic group. And again, what is this? This is like, okay, let me just say. Again, end of E is like a lattice of rank 4. Degree is a quadratic form of rank 4, but as a positive definite quadratic form. You can just think of it as Q, x1, x2, x3, x4, a quadratic polynomial with integer coefficients. Quadratic form, positive definite, so it only takes positive values. It's only 0 when all the components are 0. So every time I have to compute how many elements I have in this lattice which have Q of x equals n, I will have only finally many of these. And then I'm looking at this in this space, let's say Re, and Re is a p-adic completion of my lattice. So it's like the same thing here, but tensor with set p. Okay. And then one can try to study this problem as just a problem about quadratic forms and distribution of integer points in p-adic spaces. This is what is called Linux type of problem. So in general, people have studied the distribution of integer points that represent some n under some quadratic form Q, and the distribution of these points in Euclidean spaces. So Linux problems. This is again Q, positive, definite, integral. Let's assume even primitive, whatever we need. Let's say rank n, at least 3. And then we look at, this is in some lattice L isomorphic to set n. So we have a lattice and we have a quadratic form. We want to understand the distribution of q to the minus 1 of a given n, which is just the number of points in my lattice such that q of x equals n. It's a finite set. And typically, people study this problem in the Archimedean setting, which means these are points in some lattice, and then I think of this lattice as lying in some Euclidean space. So if I tensor with R, this will be R to the n. What people do is the following. They consider, this is the classical approach, they consider the map that goes from Rn to the sphere in dimension n minus 1, which is just take a vector non-zero and map it to x over the norm of x. That is just a projection map to the corresponding sphere of dimension n minus 1. And what people do is prove equidistribution results. So typically, under some assumptions about the quadratic form, these sets of points will become uniformly distributed with respect to the unique measure on the sphere. Oh, is that correct? Sorry, maybe I'm doing it in general, so I have to divide by square root of qx, I guess. That will go to the sphere associated to q, which means the elements in Rn which have q equal to 1. And actually, to be precise, sometimes it's not a sphere. It's more like an ellipsoid. Okay? So what I'm doing here is projecting all these points to some compact space, this ellipsoid or sphere, if you want, associated to q. This is a nice surface of dimension n minus 1. And people prove uniform distribution results with respect to the unique measure which is supported on this set, which is invariant under the corresponding orthogonal group of the quadratic form. And so there's some Archimedean equidistribution result. So in the Archimedean setting, and these are due to a bunch of people, depending on the rank. Larger rank is easier. So rank, well, anyways, there's like Pomerenke, and Linick, of course, using an ergodic method. Duke, using an automorphic approach, and Duke and Schulze-Pilot. So all these people have contributed to this problem, and the result is that if I should say this, if the number of points grows fast enough, somehow if we have enough points in these sets, which is not a trivial problem, I mean, a lot of people have studied the problem of counting these sets, so in how many ways I can represent n with vectors in the lattice. So if this grows fast enough, then I will have equidistribution if I put 1 over the number of elements, and then I take a direct measure at each point x divided by, what did I do? Square root of qx, if this is correct. So I project the point to this ellipsoid S, and then I take all x in q to the minus 1n. Then this will converge to the, I will just write like the Lebesgue measure on this surface. But this is the Archimedean setting. Here we need a p-adic analog. And that p-adic analog was not known when we were doing this. So we had to do it. So we had to prove a p-adic version of this kind of result. And I'm just going to say that that kind of p-adic analog exists. But you no longer need to project. You don't need to do this, because everything lies in this set p, in this case set p to the 4, but in general set p to the n. And that's already compact. You don't need to do a projection because points are not escaping. So what we proved is that there's a p-adic Linick kind of theorem which says that if, let's say, n goes to infinity, here is implicit that every time n was going to infinity, if n goes to infinity, but n also converges p-adically to some L, let's say a unit, and the orthogonal group of my quadratic form, the p-adic orthogonal group of my quadratic form acts on the corresponding sphere or ellipsoid, the p-adic one. So I will put L, Q, L. This is by definition all the points in my lattice tensor set P, such that Qx equals L. So this is like the p-adic version of this kind of thing, of this ellipsoid. If I have an orthogonal group that acts transitively, then you can push the hard measure here to this set. You just project the measure. So there is a unique Borel probability measure on the p-adic sphere that is invariant under the action of the orthogonal group, and there is equidistribution of these points with respect to that measure if the number of points in q to the minus n grows fast enough. So I put the same delta, but as I said before, I don't need to project them to this unit ellipsoid. I just keep them as they are, and then this will converge to this Borel probability measure. I didn't put a name. Mu q l on here, and then I have to put mu q l. Okay, so this became apparently a completely unrelated result. This is only about quadratic forms. This is only about integer points that become uniformly distributed in some p-adic way. But now we can apply this general result to the setting that we had before. So now apply this to this set of endomorphisms of E inside this lattice. So this is a rank 4 setting. And then in order to describe the limit measure associated to the Hecke orbits, or the uniform distribution of Hecke orbits, then what you have to do is kind of push forward everything from this setting, from this equidistribution result in this setting to the original space. So somehow you have to go back under all this construction that I was doing before. I was changing this space BE by a formal thing. I was constructing a group acting, and I was instead of looking at the orbits, Hecke orbit, I was looking instead of that to I was looking at these things. And then at the end, as I said, TNE was essentially and E acting on the formal group. So basically the result for these guys, you have to push them to these sets. And there's no really much better description of the result. So I would just leave it like this. And what's going on is that we are going to get like a small compact subset of the supersingular region, the locus of supersingular reduction, where we have this Borel probability measure, which is the push forward of a measure defined on this p-adic space. And this compact subset, it's contained in CP. You don't have to go to the Berkovich space. And hence, this limit measure is completely different from the direct measure that we got in the Berkovich space. So this is a completely different result. And that's why we cannot talk about really uniform distribution of general Hecke orbits. There's like a family of measures that you can get at the end. And my time is, okay, I'll stop here. Thank you.
Are there any questions?
So for each L, you get a different
Yes.
distribution.
Yes.
And so you limit this, you don't have a limit.
Yeah.
Depending
Yeah.
on how you move it in? Or?
Here, yes. In this setting, in this p-adic linic, definitely. Because if I change L, I get a completely different support of my measure. So here it looks like you have, your measure will depend on the limit L. But when you do Hecke orbits, you can show that, okay, here they are different. Once you project and you act on this guy, they will become not all the same, but only two options, depending on whenever this is a square or not in here. And P, I'm assuming P is odd. But yeah, that's a very good point. Here it looks like infinitely many possibilities. Here you have only two. Yeah. There are two Hecke orbits. We call it like the square Hecke orbit and the round Hecke orbit. No reasons. But there are two. There are two disjoint.
Square and non-square.
The square and non-square. You got it wrong. Yeah. Yes. Jan?
Any more questions?
Yeah. Oh.
I don't know if this is a kind of a basic question or not, but the measure depends on the action, or is that a canonical action you're taking?
This is a canonical action because, sorry, I went really fast and I didn't define things properly. But the orthogonal group is a group that is naturally attached to the quadratic form. It's the group of all linear transformation from this space to this space, which preserve the quadratic form, right? And here we are assuming, well, it's a simplifying assumption, but it's assuming that the action is transitive so that you get a unique measure that is invariant under the group. Everything here will be quite local. So this is it's like set p to the n. So what you can do is kind of take reduction mod powers of p, and then you have, I don't know, 20 residue classes, and you put the same measure to every residue class. And you do the same for every power of p. So it's really the uniform measure that puts the same mass to each piece. So it doesn't really depend on this. It's just a way of saying that this measure will exist. It's the push forward of the hard measure here. That's one way of putting it. Jan,
So, well, I have a couple of questions.
Yes.
But, one is maybe, do you know, because here in the whole setup, you consider modular curve of level 1.
yes.
So it's a projective line. Do you know what happens if you add level structure at?
I think,
Half p squared or something.
oh, you want to add p to the level.
Yes.
Yes.
Of course, I want to ask the most annoying question.
Yes. no, it's the most interesting case. I remember we didn't, we talked about it with Ricardo and Juan, but I think there's interesting things happening there. I still don't know what's the general picture, but I remember like even in doing like TP and so on, you can have more than one point in the Berkovich space that describes like the asymptotic distribution of the points. I'm trying to remember how this goes.
But your argument in the ordinary case is probably less sensitive to this increase in level structure, I would guess. The supersingular case will be very different.
I don't have an answer to that,
Okay.
but
Well,
interesting
it's
question.
probably quite difficult, but there's no results so far.
yes, I don't have an answer to that. So it's open, but I don't know what happens in level P. Yes.
Maybe I have a much more basic question.
Oh, thank you.
So in the ordinary case that you
Yes.
discussed before, you showed that if you take a ball of radius less than 1,
Yes.
points eventually move outside of it.
Yes.
And there's still something I have to wrap my head around as to how that translates into a statement on measures. But could you maybe clarify which Gauss point the measure will converge to?
Is the Gauss point associated to OP, to the unit disk?
Aha, so it's the one of the boundary that you get when you take out the disk around the point infinity, so the bad disk.
Yes.
I see.
Yes.
So there's no accumulation around the Gauss points where you take the supersingular disks out.
Can you repeat that?
Well, the ordinary
there's-
locus, the way I see it, is it has this bad disk in it, but it, right?
Yeah, the bad is not like what I was defining bad.
No, exactly.
That's the bad. Okay,
exactly the same.
The
So
neighborhood of infinity, kind
the
of.
neighborhood of
Okay, okay,
infinity,
okay.
and you also have the neighborhoods of the supersingular.
Yes.
So you take away all these disks,
Yes.
and that's the ordinary locus. And so you're saying
Yes. Yes.
that your result implies convergence to the measure that is the Gauss point of the bad disk. Is that what you're saying? And not the Gauss point of any of these supersingular disks.
Is the Gauss point of the bad?
The bad
Yes.
disk, I
Yes.
see.
Yes. Yes. It's
Great.
just one canonical point. It's the same one for all these results, and it's the one exactly the one that you say.
Okay.
Yes. When you remove the bad part, what is left is the union of the ordinary and the supersingular,
Right, exactly.
and then for me it's always OP, just the unit disk. Yes.
Any more questions? So let's thank Sebastian.
Thank you.
once more. We'll have one last coffee break this
Okay,
week.
cool.
But before
Thanks.
going there, I would like to thank the organizers
Yeah, definitely.
for putting
Yes,
up
yes.
so much hard work preparing the event. And we hope to see you again next week.
I hope that too.
Puede fallar de ser tránsito.